I want to start my talk with some introduction and some information about the telescope that's coming on top of Haleakala here, and that's the construction site probably 2 weeks ago or so. So it's getting real, and the other image is kind of a model of the instrument that we are building here at IFA. Actually, there are 2 instruments being built by the IFA for the telescope, but I'm going to talk about CryoNersp here. And in fact, we started officially construction for that instrument July 1st this year. But that was actually my first contact to Maui. It was 2011, and that's probably what people in Europe think about Maui or Hawaii in general. And that some pictures from my first visit here was actually a conference, so they really picked the nicest possible spot to have a conference here. And well, I was always looking kind of I knew that the telescope is coming, so I keep looking for whether there's any opportunity to get a job, to do some work here. And it turned out the timing was perfect. So we moved from tiny Switzerland to the tiny islands of Hawaii. In fact, the state where I lived is probably the size of Maui. So, and here I got a picture. I borrowed a lot of the pictures from the NSO website, which has all or even more information about the, here it's still called ATST telescope, and that's just a model at top of Haleakala. So let's see what's inside there. Got a really tall building, which is about 45 meters high, and telescope is sitting up here, and the instruments are going to be down here in this lab space. So light is captured here by the primary mirror and then transferred down to the laboratory where our instruments will be located. The kind of design for the telescope is new. So with most other telescopes, the secondary mirror would sit somewhere in front of the primary mirror here and cause some scattered light. And with that new design where the secondary mirror is kind of to the side, so we use an off-axis parabola mirror, which is kind of just a section out of a bigger parent. So that will basically focus the light off the incoming axis. So we can avoid a lot of stray light with this type of design, and that's especially important for our instrument because we want to look away from the sun and basically observe the atmosphere of the sun. And the atmosphere of the sun out there is really faint. So we don't want to have a lot of scattered light from the disk or the sky. So we really prefer having this design. Another fact is that the primary mirror is 4 meters or 13 feet in diameter. So that's a really big mirror for a solar telescope. The other telescopes solar telescopes that are around have maybe 1.5 meters maximum. So that's a lot bigger than other telescopes. One problem that we get by capturing so much sunlight is heat. So the mirror might heat up, and then there is up there is a field stop which allows us to, we're basically using only a tiny amount of the light that we are capturing, because we want to look at a small patch of the sun. We don't look at the whole sun. And the remaining light needs to be deflected and basically destroyed somehow. So we get a lot of heat. And we need to cool all the structures, so there's cooling involved here, and that's the mirror cell where the primary mirror is sitting on, and all these pipes, these big pipes, are for cooling. Then there's other cooling involved with the whole building, so we don't want to have the building structure heating up, because that might the whole structure bend, or if other parts of the inside of the building heat up, we get convection. So the air is moving inside the building, and you might notice when you walk on a hot street or a highway, that the air is kind of wobbly there. So that would be basically the same effect, and we don't want to have that. So the telescope project really cools or stabilizes the air and temperature of the whole building. Over here, that's a blank for the primary mirror that is now being polished in Arizona. That's a special kind of glass. It's called Cerodur. That's the specialty for this glass is that it has a very low thermal expansion coefficient. So if it's heated up, it won't change its size a lot, just by a tiny amount. But still, we want to cool it to stabilize it. It's a type of antifreeze, I think they're using for the cooling. It's kind of a glycol. I don't know the exact type of alcohol they're using, but that's what's in there. So I jumped one slide. And that's another really nice feature of the DKIST telescope, which is a adaptive optics system. So that's a mirror, and what you see in the back here are actuators. So with these actuators we can kind of bend and deform these mirrors, this mirror here, to correct the image. It's not so clear, it's much more clear in the next movie that I have. But this one is without the adaptive optics turned on, and that's a slightly better image. And the circle here is actually the size of the Earth, just for comparison at what features we are looking. And that's a sunspot over there, so it's even bigger than our Earth. And that's a quick overview what the adaptive optics looks like. So that's without any correction. We can't see very much, and that's with the system turned on. That's a movie from a German solar telescope on the Canary Island. I have to show these movies because a DKIST can't show the movies yet, right? And this is all due to turbulences up in the atmosphere. So the way it works is that the incoming light is kind of distorted. So we have a deformable mirror here. There's a beam splitter, so we use a little light for the wavefront sensor, and the rest passes through and can be used for any experiments. And what the wavefront sensor then does is kind of produce, here are actually 4 patterns. They're different, but they should be the same. So what the wavefront correction then does is bend this mirror to correlate these patterns, so we get a much more stable image that we can use to do science with. And as I said, it's really real. That's the enclosure structure. I think that's back in Spain, but it has been shipped and it's stored somewhere down in Karlui already. Some parts are still on a boat, but big part of the enclosure is already on Maui. Up here, that's the actual telescope mount. So down here is the primary mirror sit, and the secondary is then up here. This structure has been tested as well, as has the lab space. We call it Coude rotator. So these concrete slabs here have been put on there to test the lab space, just to simulate the weight of the experiments that we are building. Rockford, okay. Illinois. Mm. And that's in Arizona, Tucson, where the primary mirror is polished. That's a very technical support for the blank where the mirror is sitting on. So there are already actuators there in the back to support the primary mirror. And now maybe why are we doing all this, right? So we're building a very advanced telescope on the summit here, and I have put together some images I like. This one is from a total solar eclipse. That's actually made by an amateur observing the sun during a solar eclipse, but you can see that the moon covers the disk from the sun, but there is a lot of structure out there in what we call the corona. This is also a corona image, but from a satellite, and you can see all these loops, and there are magnetic fields involved on the sun, and we want to understand, or would like to understand, how these work. So people are using computers to simulate what's going on the sun. But right now the resolution we get with our telescopes are just not enough to resolve the details we want to know or need to know to better understand the processes. Here's a close-up from a sunspot. There's a lot of dynamics going on in here, so if this would be a movie, it would move and like water in a kettle. It's moving, it's bubbling, and we need to have, or you want to get some closer look at these dynamics as well. And this one is another faint structure in the upper atmosphere of the sun that we can study. And that's actually taken with a test filter for one of the other instruments that's coming for the telescope. Right, and the goal is to resolve structures on the sun on the order of 70 kilometers, 44 miles. Not really big, so we really get to see a lot of details with the telescope. And this is just another overview about the wavelengths that can be observed and kind of the spatial resolution, the details that we can observe on the sun. You can see there are a lot of satellites and telescopes over here, and DKIST is kind of getting into that space where nobody has observed before. Well, that's my quick introduction of the telescope itself. Now I want to talk about our instrument, the instrument that we are building here. It's called CryoNIRSP, which stands for Cryogenic Near Infrared Spectropolarimeter. A very long name, and I want to. I have a slide for each of these words in the presentation. I don't know when exactly, but Jeff surely knows the design started for these instruments. Could it be 2004? Could be. So many people have thought about this instrument already before I joined the team. In fact, there was an early design review in 2011, and I started July 2013 working on that project where we finalized the design and produced a lot of documents for comparison from the space experiments that I have done before. We haven't made or produced not as much documentation as we did for this, and that's just a design document. There are other documents for software, but that's just the way the project makes sure we spend the money wisely, right? So we don't waste any money. And as I said, by July 1st this year we started construction and are just about to order this big box from our colleagues in Tucson as well. They built the whole mechanical outside, the vacuum case and all the mounts that come with it. Here's a quick summary or an overview of the different instruments that will be present or the first generation instruments that will be at the telescope. So here it's kind of the spatial resolution, the details that we can observe, and again the wavelength, where CryoNIRSP is kind of occupying a space that goes much further into the infrared than the others. The other instruments will have the support from the adaptive optics system, so they can resolve much more detail than we can. Only at the very long wavelengths we will be able to kind of get the maximum out of the telescope. These are kind of other images from the sun, which this is a composite, and that's basically the field of view that we can observe with our instrument. So it's really only a small part of the sun, and we will be able to kind of see, that's just the enlarged area where we can observe these loops within the corona. Let's start with, I left out the cryogenic first, but let's start with the infrared part. As most of you know the rainbow colors, right? And just a little past the red, we get to the infrared, which is basically heat radiation. And I went to the lab and used our infrared camera to take a picture of me with a ordinary window glass in front of me. So that's a really interesting property of window glass. It's not transparent for infrared radiation. So we want to avoid at all cost having elements, transmissive elements, where the infrared radiation has to go through. So that's why we designed the instrument mostly. We couldn't completely avoid it, but mostly with mirrors, where it's just reflecting the infrared light. And this plot here shows kind of the brightness of the sky, which is this black line, and the brightness of the outer atmosphere of the sun. And in this range between 3 and 4 microns, the corona is actually brighter than the sky. It's kind of hard to imagine. It's like looking at the night sky and seeing stars. So we can see the corona through the day sky, basically. Now I'm getting to the cryogenic part. We operate the instrument, or the main working surface of the instruments and all the optics, at 70 Kelvin. I put the Celsius and Fahrenheit here as well. And the reason why we do that is, as I said, infrared radiation is thermal radiation. So everybody, like me in the other picture, emits infrared radiation. And if we have an instrument sitting at room temperature, we get a lot of infrared background from just the warm instrument itself. So we want to cool the whole instrument, or at least the insides, to very cold temperatures, so we don't get the background. And that's kind of the cooler that we are using, which is giving me a headache right now, because it makes some squealing noises. So that's another part that I learned here in Hawaii. It's kind of hard to get things repaired. We have to ship them back to the mainland. What was actually the same thing with when I moved here with my boxes. It took them a long time just from the mainland to here. And the way that cooler works is actually we have a compressor which uses a large amount of energy. I wrote down the number. It's something like 9 kilowatts. That's something like 9 standard room AC units. It's just one compressor. In the end, we will have 3 that run all the time to cool our instrument. So that's another big issue for the telescope up the mountain, actually, getting enough energy up there for their cooling needs, but also for our cooling needs. And I put a little sketch here how the cooling really works. So we get we're using helium gas at the high pressure, so that the helium gas gets in here, is at room temperature basically. Then in here is a kind of a displacer moved, and the gas passes through it. It's like a sponge. So by doing that, the gas gets cold. Now it's at the cold space, and then we can kind of close the high pressure valve, open a low pressure valve, and then the gas expands. And by doing that, it cools, and that's the whole cooling power that we get from the helium gas. And then it's just moving the displacer back, having the gas back there, and then start the cycle from the beginning again. So the whole cooling power is coming from gas expanding. And we have 2 stages. One here, the tip is going to be 10 kelvins cold, and the other stage is something like 45 kelvins. Now you might wonder, well, you're operating at 70 Kelvin. Why is that? So we lose some we get a kind of a thermal gradient. So we get it's like an electrical resistance. So we have a higher temperature after going through all these copper straps, and they're actually flexible, and that's a really important part of the instrument. We can't just bolt this plate to the working surface up there, because once we pull vacuum from our case, the whole unit will move up slightly, and that would just really push against the working surface up there. So we have flexible connections. Let's do the spectrum quickly. Some people know that one can use like a prism, piece of glass in a triangular shape, to split up solar light into rainbow colors. But as I said, we want to avoid having the infrared light going through a glass piece. So we use a diffraction grating that's reflective, and it's kind of works pretty much like a CD that produces colors. So there are many tracks on these burned on these CDs, which give like a fine grid of lines on that surface, and when the light hits that surface, it's split up into different colors. And again, we're using that part up there, which is not really visible to the human eye. Now comes the hard part, the polarimeter. What's that? I have found a nice sketch. So we tend to think about light in terms of waves, and these waves can be either in a horizontal plane, or here shown in a vertical plane. And then we can use devices that look pretty much like a fence to block the horizontal light that doesn't go through there, but the light that has a wave that goes up and down in this direction may pass this device. And it's a really nice feature. I like my polarized glasses for whale watching, right? When the sun is hitting the water, the light gets partially polarized, and if we are using polarized glasses, the reflected light will be, or partially at least, blocked, so we can get a clearer view. And why do we actually want to measure polarized light? Well, from the amount of polarized light that we can measure, we can actually go back and find out what the magnetic field on the sun looks like. So that's why we want to measure polarized light. And now back to the troubles we had. Well, we presented our design, which were these two big doors, and there was not enough money to build both of them. So we had kind of to reduce the design to this big box, which is the same as this one, and the smaller one. And this one is actually already in our labs, and I really had some fun with it. We call this one the spectrograph, and this one is a context imager. Here again is the field that we are going to observe, and in order to really observe a spectrum with the spectrograph, we need to have a slit. So if we would just observe the whole area with the spectrograph, it would mostly be just a white patch of light. But if we really get a slit, we can really produce nice spectral lines with the spectrograph, so we can really distinguish the different colors. But we also want to know what structure are we really observing with this slit? So we have a context imager that really takes an image of the whole area, so we can see where the slit is positioned in this field of view. This is just really to show you how the design or the design phase worked. We have kind of estimates for the signal that we are going to measure. That's for the spectrograph, and that's for the context imager. And the red or orange curve here is the background that we expect from the warm mirrors up the telescope mainly. And then we had the D-scope, and that's the new context imager, where the total background intersects the signal curve somewhere around 3.5 microns. So the D-scoped context imager isn't as good as the initial one, but we still can use it to get our science. And from the spectrograph, I can only show the models that we have. We are just about to order it. So, but that's what it looks in the inside. We got a couple of mirrors. The slit is in this wheel back down here, and the light is entering from here, going to this fold mirror, goes up to here, is collimated, goes to this fold mirror, hits the grating, goes to this camera mirror, and that's where we take the image with our detector and also do the whole polarimetry for the signal that we get.
Excuse me, if this was designed in 2004, things must have changed a lot. So aren't you using old technology to try to look at stuff? I mean, 10 years is quite a long time in science.
Okay, the question was whether this is the design from 2004 and whether we are still using old technology. That's the design from 2013. So it evolved clearly, so we made changes, but that's the latest design that we got from 2013, and that was approved, and that's what we are going to build now.
Where is that going to be built?
The mechanics will be built in Tucson, Arizona. There's a company there that only builds this. They're basically vacuum cases, right? We need to evacuate them, so pull all the air out of it, and then there are the coolers underneath here to cool the whole structure here. Just about the size. The length is about 2 meters. That's 7 feet, and the width is something like I got the number somewhere. Is about 4 to 5 feet wide, and the weight is 2,400 pounds, just for this box. So that's why they use these huge concrete slabs on the side to test whether the whole structure moves as it should. Well, that's the model, right? But I got this little guy in the lab. Initially it was thought as a test device where we could test all the mechanisms and cameras that we want to use, but now it's going to be part of the real instrument. So, this device is also really helpful, or helped a lot for the experiments that we did. It's called a laser tracker, and it uses this kind of reflectors there are basically three reflecting surfaces that are all perpendicular to each other. So a laser beam hitting this cube is reflected back the way it came. So, and the laser tracking device has a head up here that moves, turns around like this and up and down, so it can measure angles, and up and down and to the side angle. And it also can measure how long it takes for the laser beam going from here to the cube and back. So it can calculate the distance very accurately. The accuracy is about 20 microns, which is a fifth of a hair thickness. So it's pretty accurate for absolute measurements. And if you're doing just or compare two positions to each other, it's even more accurate. One of the interesting tests I could do with this thing was vibration testing. The company has a really clever way of designing a mount for that cooler that I showed you earlier, because there's something moving in that cooler up and down with a frequency of about 1 second. So it's got and this produces vibrations, right? And vibrations are really bad for our detector. So they came up with a really clever design with these vacuum bevels, a big one up here and then 5 smaller down here. So then if we pull out the air of the doer, this plate where the cooler is attached to is kind of floating. It's balancing the gravity, so the weight of the weight force of the cooler is just controlled by basically the diameter of these bevels. So it's supposed to float there, so it's kind of moving there and not shaking the whole doer. And that's what it looks in real. But unfortunately, it wasn't as stable as we thought. So we saw this spike, so that's really the 1 second spike that the displacer does inside the cooler. And the amplitude is kind of roughly 30 microns. And the interesting part is that the pixel sizes of our camera are 18 microns. So if we get these vibrations on our working surface, the whole image is shaking like somebody trying to take a picture with a camera, but shaking a lot, right? And that's just a way of analyzing which frequencies are in this signal, and that's really the 1 hertz peak from the displacer that we had or that we have in the cooler. And that's the heart of the imager, basically. Up here is the camera. There's a plate on the front side just to protect the array, and the light would come in from the front here. And if this plate here is shaking with these large amplitudes, we get a blurred image. So that's where the investigation starts, right? And 2 things were really obvious from the beginning. So that's basically the marks that the bolts that are here made. Once the vacuum was pulled from the door, the whole cooler would move up and push against this surface from underneath. So we had to grind down these bolts to get rid of these vibrations. And another source for the vibration was that this was basically thought as a light shield. Infrared measurements are really sensitive to stray light that might come in through any gaps that are inside the design. So we had this shield around that structure here, but the shield would touch, and it was attached, bolted to this plate underneath, and would touch the other plate up here, totally destroying the purpose of these flexible links, right? So they can kind of compensate for the vibrations, but not if we are touching there. But these weren't all the sources, so that's really where I spent probably 2, 3 weeks, 4 weeks finding the last source of vibration. And imagine you have to cool down the whole system for 1 or 2 days. Then you can do the measurements. Then you have to warm it up again. Takes about 3 days. And then you can disassemble the whole thing and look for other sources. And that's the last source. I've enlarged this one here. This is another light shield, and that's a mechanical feed-through that goes straight to basically, again, the cold working surface that we have. And it was designed not to touch this plate, but again, when the cold head is pulled in, it's not straight up, it's kind of tilted. So this edge would touch the this light shield once we have a vacuum. Was kind of, because when I opened the door again, it was not touching at all, because it was designed this way. But after eliminating all these sources, we got down to a noise level of 5 microns or so peak to peak, and this 1 hertz peak is now gone, and we have a no vibration issues anymore. Another experiment was with a grating stage that we have. That's just a large piece of aluminum that simulates the weight of the grating. We have a mirror up here. Here's the laser tracker again, so we can shoot the laser beam off this mirror back to the corner cube reflector back there, which is about 30 feet away. And the really interesting part is that we want to measure really tiny rotations of the grating. These are some of the results. It's just really interesting that having this, so here's the tracker. This surface is basically the mirror that I showed you, and back here is the corner cube reflector. But for the laser tracker, it looks like the corner cube is back here or over here. And by measuring angles, we can really distinguish really small steps. So the rotation was, in this case, 1 arc second, which is 1 degree. So one whole rotation is 360 degrees. Then we split it up in 1 degree steps, and then we split it again into by 3,600. So that's 1/3,600th of a degree. Really tiny rotations that we want to measure. And that's just to place the right spectral line that we want to measure onto our detector. And eventually we want to measure even tinier steps, but right now the gears inside the mechanism are just not fine enough, so we can really do that step size. We have to wait for custom-made gears that we can use to rotate the whole stage in even finer steps. Another interesting experiment that's just about to start. It's set up, it's a large styrofoam box, and you have no idea how hard it is to get a styrofoam box that size. It's 20 by 20 by 20 inches. So I tried all the fish companies on the islands. we ended up shipping one box which costs $35 from the mainland. And obviously it comes by ship, so it takes 5 weeks. But now it's here, and we got liquid nitrogen that we want to get into that box and cool the stage down. We had some fun with the grating. That's actually the size of the grating, 1.5 by 1 feet or so. That will be used and was tested just with a monochromatic source for efficiency. We have a that's a real image from our detector that we are going to use. Looks not so nice, but we can correct for most of this. This is just a raw image, and that's a soldering iron. That's just an infrared image, a soldering iron imaged through a pinhole, so we could get kind of a test image. And another part, I was already talking about light leaks, so I had to put a lot of aluminum tapes around over gaps that we found. And how it works is really we switch off all the lights in the lab and use a tiny torch, place it somewhere and see whether there's any light coming through. And that's another example. There is light just at the edges of these inserts coming through. So we had to close these gaps as well. Otherwise, the detector sees a lot of background from the instrument, from the warm housing of the instrument itself. What else do we got? And that's just, I think the data curve is so big. There we go. Another issue for the telescope was that that's basically vacuum. So we the initial plan was to run the vacuum pumps all the time, but they don't like that because it's vibrating and it's using power. So we had the test tour down here running for about 3 months without the vacuum pumps running, and the vacuum kept perfectly. So we think we can run the instrument without having the vacuum pumps turned on all the time. And that's just the cool down time to show. Takes about a day to cool the small doer. The bigger one will take a little longer, maybe 2 days. And then we're down at the temperatures where we can work. So it's really kind of a process. Whenever we want to change something within the doer, we have to warm it up, open it, and do the work and hope we did it right. And a lot of fun stuff that's coming up with the spectrograph is the alignment, because to get the optical system working, we want to place the mirrors really exactly. But the problem is, once we cool the instrument down, the surface is contracting. The mounts from the optics are contracting. So we really need to align it warm and then misalign it, so it will be in the right place once it's cooled. And there the laser tracker will help a lot to get this right. Right, and that's all I have for tonight. Yeah.
I have a question. Since the U.S. is trying to get rid of its helium stores, because there's only one large place where they have them.
Right.
How much helium do you lose, and how much do you need on a yearly or monthly basis?
Right. So the question is, how much helium do we need or how much do we lose on a yearly basis. I knew there is a kind of a helium
Repository.
yeah, but it's kind of harder and harder to get helium, right? I know this from diving because some divers use helium to really dive deep, and it's harder and harder to get helium. But our system is a closed system, so ideally we don't lose any helium, and we only have to replace small amounts when we do servicing once a year. But it's supposed to be a closed cycle. Yeah.
So the sun is going to come in and it's going to leave it here and here's going to get out, right?
Right.
But you have to cool it off with the refrigeration system?
Okay, so the question was whether we have to cool the mirrors because the sun will come into the instrument and hit the mirrors, right? And the question is whether they heat up enough, so we need to cool them. The cooling system is running all the time, so we can continuously cool them, but the mirrors are highly reflective in the infrared, so it's probably 99% of the light is reflected and doesn't heat the mirror, right? And the remaining 1% is the cooling system efficient enough to cool the mirror there. Yeah.
When the sun is up in the sky, I was still looking at the sun. So what degree
Okay, so the question is from what elevations we observe the sun with the coming telescope, and plan is from horizon to horizon. Yeah.
What process do you use to dump the excess light? You're saying you have to destroy light.
All right. So I
Process is-
yeah, I think it's like a mirror that reflects into a big black box that's cooled.
literally just dumping it there.
Right. Yeah, but it needs to be cooled very efficiently. Yeah.
If you're gonna track the sun from horizon to horizon, do you need to correct the optics for when you're oblique through the atmosphere versus straight overhead?
So the question is about diffraction inside the atmosphere, whether we need to correct for that. That's probably up to the people that use the data in the end, right? I'm not aware yet that we are correcting for the initial product for the diffraction. We might. Yeah.
How do you affect, or how do you account for possible seismic tremors that may occur while you're observing?
All right. So question was about earthquakes. We had to provide for the design phase a seismic analysis, and we're in pretty good shape. So the safety factor is something like 4 to 10. But we had to provide a seismic analysis, so all the optics are basically retained in place. They can't just drop out of their mounts. But that's one provision we have. So there are tiny clips that hold the optics in place. Yeah.
My question is that the phylogenetic systems, what you're using, is that only liquid nitrogen?
Okay, the question is whether the cooling system uses liquid nitrogen. We don't use liquid nitrogen. It's helium gas that we are having in a closed cycle. So we have the compressor that compresses the helium gas, and then it goes through a pipe to the cold head, and inside the cold head it expands and it cools at the place we want to cool, and then it's returned to the compressor, compressed again. We had initial plans to use liquid nitrogen for pre-cooling, but that's kind of a safety issue. then you have to have burst valves, and because if for any reason the instrument heats up, the mechanical coolers have no power, so the whole instrument might heat up. Then we might run into trouble having liquid nitrogen within the instrument, because it expands and could basically destroy the whole instrument.
And kind of connected to that, you mentioned something about the cost of energy that you have to incur up there.
Right.
Now, this is kind of a duh question. Are you too much clouds going in and out? Can't you use like a photovoltaic to give you some type of power? So they use solar energy.
Right. So the question is whether we use or could use solar energy for powering all the devices. Right, and that's a little over the top of my head because I'm not involved in the project itself at the level of building the telescope itself. I'm just providing the instrument, right? But it's surely a fair question. A question one would have to ask the people from. You know the answer?
He actually uses a lot. This instrument he's building uses more power than all of the energy that's all up here. So it's not enough. Is the main. It's not enough power. Even if you took all the 99% that we're throwing away and disposing of, it's not enough power to put power on this instrument. They don't like this very much because we're using so much power for his big compressors and refrigerators.
Mm.
Which is why they complain at us. They gotta turn our plant off. Electrical power.
Who's they?
Mine-
I was gonna ask that.
They is just a
project.
Nico.
Well, one of the things that we are doing is that we have an ice plant that makes ice at night during off-peak hours, and then they circulate the glycol through the ice during the day. So that way we can make better use of the energy generated by the windmills over the West Maui.
Yeah. But that's for the telescope, right?
For the whole
Yeah.
thing, right?
Yeah. Yeah.
How much does the mirror, the 4-meter mirror that's being polished in Arizona, how much does it weigh?
The weight. That's so so the thickness is 3 inches. Right.
After a beer.
It's 7 tons of weight.
Yeah.
7
Yeah.
tons.
Yeah.
How much does your instrument cost altogether?
So the cost for the design phase and construction phase and salaries, people, hardware. Ah.
Priceless.
Yeah, priceless for sure.
I'm just asking the instrument.
Yeah. It's,
What investment is right there?
it's 5 millions.
But the one that you're that you're building is.
Yeah. Yeah.
The whole facility is about 340 million.
That's, yeah,
So I have a question, because you mentioned that you have to get things from the mainland.
right.
And with the Hubble, the people who made the mirror messed up. So what happens when the mirror gets here and it's not to your tolerance? I mean, what sort of quality control do you
Right.
have to make sure the mirror by the time it gets here
Right.
is
So
what you want?
So we haven't decided yet on the question is whether or how we control the mirrors that we are getting are the right size and the right figures basically. Are you talking about the
Well, because in the Hubble, there was a distortion in the mirror, right?
right? You're talking
So-
about the main mirror,
Correct. the 13 meter, 13 foot diameter that you have?
Right. I think the mirror is going to be tested on site there to make sure it's the right figure, and then it's shipped. And for our instrument, it's we haven't decided yet on the vendor, but there's a company here on Maui doing mirrors, so we might use that company so we can really go on site and test the mirrors there. Yeah.
What's the final cost of the primary minus shipping? I don't get to ask what shipping is.
Yeah.
The cost for the primary mirror.
But I just worked out the math. It's about 1.7 tons. But compared to the old mirrors, it's a very modern mirror. It's a very thin mirror compared to, what's the thickness of the mirror for the AOS stoves?
6 inches.
Which is also very good for this mirror stove. 6 inches, so that's about 15 centimeters. This is less than that. It's about 10 centimeters. It's a bigger diameter mirror. So it's almost like a piece of paper in terms of how floppy it is. Which is the modern style.
And the cost for the primary mirror, I don't know, because it's not. It's kind of the telescope project providing this one. I haven't seen the number.
About 5 million. Is that about 5 million? Cost has grown.
Yes.
The Roger Angel mirror.
So how is the paint lined that you?
Well, you want to speak into the microphone?
Yeah.
You want to repeat the question?
So the question is, how long does the polishing and grinding take for the primary mirror?
JD, do we have a microphone?
Can use this one.
We have
Jeff.
a microphone?
Jeff.
Sorry. So the mirror's a kind of an interesting story because the first one broke. Well, it didn't exactly break, but they discovered as they were grinding it that it had a big crack in it. So that means it's taken a little longer. But that one actually got used then as a test mirror. So they tested some of the polishing technologies. A mirror like this has never been polished before. As Andre described, the mirror doesn't have a hole in the middle of it. So it's the biggest telescope ever made like this that doesn't have a hole in the middle where all the light comes off to the side. And so they used that broken mirror as a test. The total polishing time for the mirror, I think, so it happens in stages. So the mirror it comes from Germany, it comes from Schott, and then they do some grinding on it. And then it comes to Tucson and they do some more grinding and then they do final polishing, and that whole process takes about 3 years. So it's that's the heart of the telescope though, so that's worth it.
When is this supposed to be operational, and have you had a lot of delays? Is it on track?
Okay, next interesting question, when it's going to be online, the telescope. I think 2019 is the latest we know.
When's your instrument going to be done?
A little earlier than that. The instrument will probably be ready 2017, 18. So we have to store it.
What is your own background? Are you a mechanical engineer? What expertise are you bringing to the project? It seems pretty amazingly technical.
Yeah, I'll have a master's degree in astrophysics, and then the PhD degree was more instrument oriented, like experimental physics. So I have built prototypes, cryogenic instruments that are measuring. Well, one was a prototype to be flown on a space mission once the funding is available. It's basically measuring total solar irradiance. That's how much energy is coming from the sun. Closely related to climate change sciences. But it was mostly about building instruments.
So, I'm sorry, so what exactly, because you only showed a few pictures, what exactly will you be measuring? You said magnetic fields, or what exactly will you be measuring, I guess, in the corona?
Right, so the question is what we are really going to measure with our instrument, and that's really the main thing, magnetic fields outside in the corona. That's what we want to measure.
And that's going to tell us what?
There's kind of a thing that's not really well understood how, because the plasma out in the corona is really hot, and we don't know yet how exactly the energy from the sun is transferred out to the corona, and the idea is that magnetic fields are strongly involved there. 2 questions. Who's first?
Will you be running the instrument after it's up and running, or are you just the creator of it?
Right.
You just build it, or are you going to actually?
So the question is whether or not I'm sitting at the telescope running the instrument when it's on the telescope. At the beginning, yes. So as long as we have to set it up, commission it, we will be there. But then we have to write another manual, probably that thick, to tell the operator how to run the instrument on a daily basis. The other question?
Yeah, are there other instruments being designed and built that will operate in conjunction with your instrument during the use of the telescope?
Right, so the question is whether or not CryoNERSP is running simultaneously with other instruments on the telescope. Right now, no. All the other instruments can run simultaneously, but not CryoNERSP. So we really get a pick-off mirror somewhere in the beam that deflects all the light to CryoNERSP. And that's a decision made by the project.
If you need to order any more styrofoam boxes, you can get it faster on Amazon.
That size?
3 days. $18.
A big one like this?
I just got a box that big. $18, 3 days.
Really? 20 by 20 inches?
Yeah.
You gotta get Amazon Prime though.
Yes.
I already got an Amazon Prime account because that's something I learned. I was looking for a week probably to find one of these boxes.
We couldn't make it ourselves because it would leak out the hole.
Yeah.
Might have a solution. You have to check with the.
It's funding this.
That the whole telescope is funded through the National Science Foundation.
Oh, I thought there were several, it's a consortium, I thought, of people
I
from all
think
over the world.
that's another telescope.
Oh, that's
The organization that influences what happens to the telescope is broadly international. So, Germany contributes. Her institution is building another instrument for downstream. So there are many, all over the world, there are scientists that are involved in the construction. And some of those other countries are paying for their instruments, like the Germans will come with an $8 million instrument when the telescope is built. But our National Science Foundation is through a proposal process many years ago, awarded this contract to a number of scientist organizations, and the University of Hawaii is one of them. But the short answer to your question is that our National Science Foundation has taken on the responsibility for building this, and then the international community is involved in using it in the end. I think Andre may be around for a while. Can you stay and answer more questions?
Sure.
So we should thank him again, and thanks for coming.